Hello and welcome to part 4 of Dev Maths and Stats Refresher Course Lecture 10. Now here we're going to look at the theory and examples behind some simple tests, and in next videos I'll show you some of those tests carried out in Stata. So I think this theoretical part and the written tests you can look at really for yourself, because I think at this stage it's more important to get on to actual examples of using Stata. So here we have a situation where, in this example, you have a country that has promised it's going to reduce its emissions by 2.4%, and they're claiming they've kept this promise. Something to bear in mind here is that the claim is 2.4%, which means that the claimed increase is negative 2.4. That's what we're testing, a negative 2.4. So we've got this data from 12 randomly selected firms, and the mean of those is negative 1.425. So the decrease in these factors is 1.425, but the government is claiming it's going to be this 2.4 decrease. So if you publicise this and criticise the government to say, look, we've shown you have not kept your promise, their defence is just to say, well, it's just bad luck. You happen to choose these ones which didn't meet the target. But in honesty, in the whole country, the population average is down below this. So what you can test is how likely is that. So here we write it more formally, that you'd write down the null hypothesis would be this. The mean change in emissions for all the factors in the population is negative 2.4. And then if you do reject that, what's the alternative you're going to consider is that the mean change is above negative 2.4. And we're only looking at above because if we go and select our random group of factors and it comes out way below 2.4, then we're agreeing with the government. We're not going to be wanting to challenge them. So we only reject their claim if it's well above 2.4. So that's why the mean change is above negative 2.4 is the alternative. Then you just take the figures you have. So you've got the sample mean, sample standard deviation, and you substitute it back into equation 1 above for the t-value, which is this, along with mu is the mean, the hypothetical mean. So if the mean really is this negative 2.4, then the t-value must be this. But what's the chance of getting a t-value like that? We find it's the t-value as high above that, as high as that, is less than 1%. So it's really, really surprising. So if the null hypothesis is true, and the average decline is really 2.4, the chance of getting a group of 12 with an average decline of that far above it, minus 1.45, is really, really, really small. So we can reject the government's claim and say it's highly unlikely. It's casts serious doubt. In fact, we can, because this is so far below 1%, we can reject H0 with 99% confidence. So strong evidence against the government's claim. Okay. Similar one with one key difference here. You're in a country and the national the coffee harvest is claimed to be 233 kilograms per household. Okay, fine. You're not sure about that. You want to test the accuracy of that. So you interview 15 households, and these are the figures you get. And in your sample mean turns out to be, of these 15 numbers, is 256, which is a bit away from 233. And when you go through the mechanics, you work out that if you take the null hypothesis again, that the mean production really is this in the whole, that's the null hypothesis. So you start by accepting this. So based on that, you can then calculate the t-value. So if this is true, then you found a t-value of this, and the chance of getting a t-value of this is 0.0177. Now, when you did this, what you do here is you find the chance of getting a t-value as big as 2.686 or lower than negative 2.686. So we consider both those probabilities, more than 2.686 or less than negative 2.686. Because in this case, we are interested in the accuracy of this statement, and we would be questioning the accuracy whether we find a figure well above 233 or find a figure well below 233. So you have to consider both those possibilities. Whereas in the case of the government claim, we were only going to reject it if we got something well above, because if we got something well below, we'd be happy that they are keeping their promises, so we wouldn't challenge it. So this is what's called the difference between a one-tail and a two-tail test. This was a one-tail test where we only reject on one side. This is a two-tail test when you reject either side. And as you'll see when we do examples in Stata, Stata gives you the results of both of them. If you're doing it by hand, you have to remember yourself that when you look up the value in Excel, whether or not Excel would only give you usually, well, it depends which command you use. It gives you either the one or the two tails, and then you have to work out if you've got the correct one. So there's fairly strong evidence here because this is less than 5%. This two tails less than 5%. So you can't be quite as confident as you were with the government, but here you can be fairly confident that the evidence is against this 233 figure. It's not accurate. So in econometrics, you'll see that you often use single sample t-tests, but that's when you're using a t-test within econometrics. When you're using a t-test on its own, the two sample ones are much more useful. That's because you're very often doing this thing. You've got a scale variable like income, prices, calorie intake, attendance, test scores, all these kind of scale variables, and you want to compare that between two categories. In other words, two values of a nominal variable like gender. Are males and females earning the same? Are formal, informal people making the same income, profit, and so on? So for those kind of comparisons of two groups, two sample t-test is really much more helpful. So you can show that if you take two means and subtract them, that also follows a t-distribution, and so there's no real extra theory. It's just a t-test again, but using the difference between the means. And I'll show you examples of that in Stata. Null hypothesis is always that the difference is 0, because that's when the means are the same. Finally, I've just mentioned these, and again, I'm not going to talk through these because chi-squared tests and f-tests, they're often used in econometrics, but they're hardwired into the econometric output. So you don't do any of these calculations yourself. Doing a standalone test, like here, I'm using a chi-squared distribution to test whether the population standard deviation of two groups is the same. So is there more variation in one sort of group of enterprises compared to others? Has the variation changed among these micro entrepreneurs? So if you want to see whether variance or spread has changed over time between two groups, you can use this chi-square test like this. So it's the same thing. You calculate the chi-square statistic and look it up and work out how often you get that value. Was exactly the same, and then comparing two samples. So you're looking at, so this is a single sample one. For two samples, it's comparing two clinics. So looking at babies and looking at the BMI scores, so you want to know how reliable, how consistent is the treatment that babies getting in these two clinics, and you're trying to test whether or not the variance in the body mass scores is different between the two clinics. And as the ratio of variances has an F distribution, it turns out to be an F test. But you're not often going to run into these doing those tests on their own. And the chances that when you do, you'll remember back here, I certainly wouldn't. I'd have to look it up. What's important is to be able to interpret the output from these tests when they come up, when the econometrics gives it to you. And in that way, it's exactly the same as any other test. You just look at the p-value. Okay, finally, before we finish the lecture and go on to just examples in Stata, think about the type 1 or 2 or type 2 errors. So type 1 error is when the null hypothesis was actually true, but you rejected it wrongly. Type 2 error, if the null hypothesis is false, so you should reject it, but you don't reject it. And you can look back at the diagram to remember why they're different. So in example 2, we rejected this 233 kilogram, but suppose that more evidence comes along and it shows that actually, okay, that 2.3 was actually correct. We shouldn't have rejected it, but we did reject, so we made a type 1 error. In this one, back here, when you're looking at the idea that the capital levels, that the variation in startup capital has changed, we didn't reject that if you look at the detail of the test. what happens if later on you realise it actually has increased, or in reality it actually has increased. So in that case, you made a type 2 error because you didn't reject it. You should have rejected it and acknowledged the fact that it increased. So conceptually they're very different, and in practical implications they could be very, very different, the implications of a type 1 and type 2 error. So you need to be familiar with that terminology. Okay, so that concludes the sort of the new material side of the lecture. So we'll move now on to another video with some stata exercises or some stata examples to show you that it's much easier using stata than it is when you have to type it into Excel. But for now, thanks for watching.